In the next few minutes, I'm going to talk about characterization of conduits related to fracture network. Small-scale fault intersection and their densities can provide considerable information about fault damage zone geometry and their associated favorable locations for conduits and fluid flow. The conductivity of fracture network generally measured in terms of fracture intersections. In this animation, damage zone with points of intersection marked in red. See the flow along intersection. A set of connected fracture intersection makes a conduit. A set of connected conduits define the fracture network and fluid path. In this application, we use a special logic operator on seismic data. This operator is based on outlining the small scaled faults intersection as the main component of the damage zone distributed along the slip direction. In this example, we can see a 3D seismic block processed by the logic operator to detect the small-scaled fault intersection. The output is 3D fault damage zone and conduit map. The dark blue is absent, where intersection is absent, and red is the highest number of fracture intersection along a shear zone. The following a few slides, we will present examples for damage zone conduit map. First, the conduits are define the conduits are a closely arranged cluster of small-scale faults intersection. These conduits are directly related to dual porosity and their connectivity to dual permeability. That's an example for the distribution of fracture intersection in different rock units. That's a seismic cross-section in sedimentary rock, and the points of small-scale fault intersection. The distribution of calculated conduit intersections for different rock units. Another example is along fault zone. This is the timeline times slice, and the small scale fault intersection. Wall damage zone, where small scale fault intersection delineate main faults. Another similar examples along small fault zones. This is sedimentary, and the fracture fault the faults are clear here. It's easy to identify, but using these techniques, that's the point of intersected small-scale faults. Using this technique, it is detecting all damage zone around and within the main fault zone. As you can see, it's all detected. This example um, uh, the, the same as before, but the only difference is that the damage here is wider and with less intensity and a bigger volume. And another example for the networking and connectivity, the points of intersection calculated. As you can see here, here is disconnected, connected, so it's very good. This is high, less, absent. This is very important to know the nature of your network. That's a very nice example. It's a clear one. You can see here the fault, and here is a faulted bed. Is the detected points of intersection, calculating the damage of the conduits. We can see that we have a main fault here. The damage in the lower part is higher than the upper, and it is fractured rock units displaced, and there is other faults and damage in the area can be identified too. This a seismic cross section in a faulted area, and in that example we are using different small scale fault length ranges. That's the example in basement rock. For length ranges above or equal 6 milliseconds, we consider it small size range. We can see that fractures are restricted in the country rock around the main fault in the area, but when we are looking for small scale length ranges, bigger, larger, or equal to 28 milliseconds, we can see that we detect all main faults and clear variation in intensity along the fault core, and the change in intensity reflect variation in dual porosity and dual permeability. Here is an example in a sedimentary rock section, seismic line. We apply 3 different for small scale length range, bigger or equal to 12 milliseconds. It's very crowded, but the black means there is no fracture whatsoever, and larger or equal 20 milliseconds, that's the output, and the larger one is larger than or equal 28 milliseconds. That zone is in a reservoir rock itself. From the above presentation, we see that conduits related to fracture reservoir can be characterized by their volume, spatial distribution, changes in intensities, connectivity, coarseness, trends. I thank you for listening. Please visit us at optimalreservoirs.com and contact me, Adel, Fouly. Thank you again.